Hey, welcome to Robotics 1. We are going to talk about Robotics 1. This course is a combined undergrad and graduate course, and this course is EGR 455 598. And in this class, we are going to talk about kinematics, dynamics, and control of robots. And we are going to follow a book by Professor Nikku. Almost section by section, because that book gives you good amount of information on the topics related to kinematics, dynamics, and control. So I will use the slides, but then what I will do is work out the problems in class. We will be using MATLAB and Mathematica. So I would encourage you to download these softwares from ASU My Apps. And some of you might have taken MATLAB class, some of you might have not, but just to get you on board, the first homework, which is homework 0, is already assigned, that is on MATLAB. So I would encourage you to look at homework, and it's a very simple homework. So you will do some simple exercises in MATLAB, and then once you are done with that homework, upload the completion certificate to the Canvas. So that is the first assignment. This course, I tried to be very organized and schedule it because of the uncertainties associated with the COVID. There could be some emergencies either on the student side or on the instructor side. So we just have to be prepared for all the possibilities. So once we go to the syllabus, I will tell you exactly what we are going to study, when we are going to study, and what material and information will be covered in that particular lecture. Also, I will talk about the homework and quizzes, when the homework will be assigned, when the quizzes will be assigned, when they will be due, and so on. So let's go through the syllabus. I emailed everyone a copy of the syllabus. Also, the syllabus is uploaded on to the Canvas. So I would ask you guys to take a moment and look at the syllabus. So this syllabus is for the Robotic Systems 1. The course description is analysis and design of robotic systems, focus on kinematics, dynamics, coordinate transformation, and modeling. So we would be focusing a lot on understanding how the robot move, what are the vectors associated with it, what are the various coordinate transformation, and how do we solve this robotic systems problem. Again, my name is Sangram Redkar, and I will just tell you where my office is. My office is in Tech Center 101B. And I haven't specified office hours but usually I'm in my office all day Tuesday and Thursday. But please send me an email and then we can meet or talk or schedule a Zoom call at a time that is mutually convenient. Again, my office phone is also given. And just for this class, let me give you my cell phone. So 334-497-1911. So during the class, if you have any question, concerns, if you are not comfortable using the Zoom chat window, you are welcome to send me a text. Or in case if you get late for some reason, and then if I'm teaching and for some reason you can't get into the class, you just send me a text. That way I would be able to reply to you immediately, and uh, or you can send me a private message. But please understand that it won't be really a private message, because whatever you see on screen, the chat window, and even the students, they are all displayed onto this giant screen in the auditorium. So even if you try to send me a private message, it's no longer gonna be private. Just keep that in mind. That's why I want to give you my cell phone. Just send me a text if something, if you need to talk to me. All right. So the book is book by Said Niku, which is Introduction to Robotics, Analysis, Controls, and Application. And this book, even though we say that it's a third edition, any edition is fine. So if you have the second edition, that's totally okay, because the chapters that are included in newer edition based on the screw theory and one more topic that we are not going to discuss. The topic that we will discuss in Robotics 1, they are covered quite well in the previous edition. I just want to tell you something that probably is very useful. For this class, we have a UGTA, and his name is George. And George is here, if you know, he is here to help you. He's a UGTA, so he can help you with some homework assignment. He's excellent in MATLAB programming and MATLAB Mathematica programming, so he can help you with that. Especially but he won't help you with the quizzes. So George, what's your email? So George took this class last last year, and he did excellent. So you have to send him an email. We also have a grader. So we have a grader. And his name is Asjad. And he is online. So what I'm gonna do is, Asjad, I'm gonna unmute you for a second, and then you can say a few things about yourself and also give them your email, or you can send the email on to the chat window.
Okay. Hello, everyone. I'm Asjad Malik. I specialize in machine design and equipment design. So here I'm gonna write my email in the chat box. So please feel free to contact me if there's any concern regarding your grading. Thank you.
Okay. So Asjad's email is in the chat box. And then you are welcome to send him an email And his email, I'll just go ahead and then just write it down for a second. Okay, his email, or I can email his, or Asjad, you can send everyone an email with your email saying uh, what email, what is your email. Okay, AAMALIK3 at asu.com. I, so I just want to clarify the roles. If George is not going to grade your assignments, George is here to help and support your learning. So if you have questions related to homework or programming, you are always welcome to contact me, or you can talk to George for homework or some assignment. For quizzes, you have to absolutely work on your own. If you form a study group, talk to George and see what his time commitment is. He can schedule office hours or meet you on the Zoom and help you out with the homework. Now, for Asjad is going to be grading your homework. So grading homework and quizzes. So the way it's gonna work is I will make the exams and quizzes and homework. I will also create the solution manual or solution. I will also generate a rubric and I will give that to Asjad. And Asjad will follow that and grade and post your grades. So if you have any questions related to the grading, please send an email to Asjad and copy me on that email. So questions related to grading, Mr. Malik is your point of contact. If you need help with the material, specifically understanding some part or help related to the homework or programming, then George is there to help you. But I just want to let you know that George is not going to fix your code. So if you send George an email saying, hey, George, this is not working, can you just help me fix it? He can, but he won't. He may tell you, okay, you might want to look at it, and then you have to fix your code. But if you get a solution and then you want to say, hey, George, I'm working out, this is how the solution looks, does it make sense? He can tell you whether that makes sense or if there is some minor issue, but he will not uh, correct your code. You have to write your own MATLAB and Mathematica codes. And homework, if you need help with homework, just don't go to him and say, hey, George, how do I solve this problem? Or don't come to me and ask me, how do I solve this problem? The first question that we are going to ask you, tell us, where are you stuck? What have you done? Is that a conceptual problem or it's just some mathematical manipulation problem? So we want to see some effort on your side before we can help you. So please work with these. Yes, George would be willing to verify your homework answers because I would give him the homework solutions. But I mean, he'll tell you if the answer is right or wrong. And he may say, okay, look at this function or look at that, look at some mistakes, but you have to fix on your own. Any other questions related to homework, quizzes? So course objectives, we have to study kinematics, dynamics, and control. We have to use software, and I have to be very specific. When we say software, we plan on using MATLAB, Mathematica, and SolidWorks to solve robotics problem. Now, I understand that most of you have taken EGR 219, a course in MATLAB, but maybe one or the other reason you might have not used it. So the homework 0 specifically is to brush up MATLAB and Simulink skills. So please start working on it. It's due next week. And again, there is no final exam. It's a good thing and a bad thing, which means you just have exams and quizzes, and that will dictate your grade. We are not going to use plus or minus grading. I expect most of you to get B or an A, but 90 or above is an A, 80, between 80 and 90 is B, 70 and 80 is C, and below 60, I mean, within 60 and 70 is a D. If you need any accommodations, please let me know and we will accommodate. Now, again, the usage on electronic devices is listed. And again, the academic integrity. So I would like to specify, please do not copy. The objective is learning and we are here to help. If we for some reason find that codes are similar, that would be considered as copying. And so I don't want to get into the argument where two of us work together on this code, so we are submitting the exact same code. So that is not acceptable. So you can work, you can help each other, but at the end, your code should be your unique code, your unique program. So if I ask you a question, why is this variable like this? You should be able to answer. So that is something that you should keep in mind. So be independent, learn, and work on your own. If you need any special accommodations, please let me know. The mandatory statements on the sexual discrimination and ASU Sync courses are in the syllabus. So we are going to use the same Zoom link every time. And we will use this Zoom link, and I will be switching between the laptop and the iPad when I try to work between the examples and the code and so on. So if I use MATLAB, I will actually start displaying it on my laptop. If I use sort of a blackboard, I will use my iPad. So I just want to go through quickly, and this is the layout and this is the schedule that we want to follow. Every lesson and the chapter is listed. So in today's class on 8/20, once we review the syllabus, I'm gonna talk about briefly chapter 1, which is the introduction. Then we will start from the next class, chapter 2. And I would strongly recommend that before coming to class, just review through the slides or skim through the material in the textbook. That will help you get most of the class time. And in this class, I have given a lot of time for problem solving. And when I say problem solving, that I don't mean that you will solve the problem and I will supervise. I plan on working out the problems in class, and my suggestion to you would be work with me and focus. When I'm trying to work out a MATLAB problem, then please open up your laptops and start programming with me, so that if there are any question concerns, those could be answered in real time. So we are pretty much going to discuss chapter 2 till the end of the September. So this month and next month, we will talk about vectors, kinematics, homogeneous transformations, forward kinematics, how to solve forward kinematics problem using theory, how to solve forward kinematics problem using MATLAB. Then we will talk about Danavit-Hartenberg parameters, the theory. Then we will work out the examples. Then we will look at inverse kinematics theory. We will look at the inverse kinematic examples for different configurations of robots. At the end, the last lesson, it will be on September 22nd, wherein I will try to work out one or two problems, start to the end in class. Then the next part is the velocity analysis. In the first chapter, chapter 2, we will look at the position analysis, and then what I will do is we will extend that to differential transformation, which is the velocity analysis. And we have about, actually, I assigned about 5 lessons, even though the material in this class can easily be covered in 2 lessons. But what I want is, once we discuss the differential transformation, I want to introduce you, there will be one lesson on Mathematica software, how to use Mathematica to solve symbolic computation. MATLAB is very good for numerical calculation, but if you want to solve or generate symbolic expressions, Mathematica is superior. So one class, which is the class in October, the first class will be, entire lesson will be on Mathematica software, how to use Mathematica software and simple applications. Then after that, we will work out the differential motions problem or velocity problems using MATLAB Mathematica software. So 2 lessons will be on using Mathematica and MATLAB to solve robot problems. And the reason for that is the robotic systems, for simple robots, you can write down the equations of motion by hand. But when the robot becomes complex, it is physically not possible to do those hand calculations, and you will have to use computer software. Please recognize understanding of computer software and its application is one of the course objectives. That's why this year I'm going to spend some time in teaching you how to use the software, at least to solve robotics problem. Again, this is not a spectator sport. So when I'm teaching you software, I would strongly recommend that you do that exercise with me. Then once that is done, in the mid of October, we are gonna move to dynamic analysis. And in dynamic analysis, there are 2 approaches. One is Newton's law. I will give a brief introduction to Newton's law and the Lagrangian mechanics, but then most of our material will be discussed using the Lagrangian mechanics. And typically, when we try to solve the problems using Lagrangian mechanics, simple problems you can solve by hand, but complex problem we have to use a computer software, Mathematica or MATLAB. Then later we are going to do static force analysis. Then we are going to spend almost 3 lessons, 10/22 to 10/11/3. So basically 4 lessons on solving dynamics problem. So we will solve at least 7 to 8 robots from start to finish by hand and then by using Mathematica and MATLAB. So that should give you a very good understanding of how to use computer algebra to solve robot problems. Then we have trajectory planning, which is chapter 7 from your textbook. So Usually the theory will be discussed in one class, and two classes are assigned for problem solving. So we'll initially solve simple problems by hand, and then we will solve complex problems for multi-degree of freedom systems using software. Then the last chapter is on the motion control theory. So we have the dynamics or dynamical systems of equation. So we know this is how the robot is supposed to behave under the action of gravity and forces. But we want that robot to be controlled. So what type of controller we are going to use to control the robot? Whether it would be a linear controller, whether it would be a non-linear controller, whether it would be a combination of those. How do we make sure that certain performance specs are met? So we are going to start with very simple linear system theory. If you have taken the transforms class, or you are currently taking the transform class, the material is similar to the Laplace transform and transfer function, but I would heavily rely on MATLAB to solve Laplace transform equations. I would use Simulink and MATLAB to solve root locus, PID, and other examples. Then we have Thanksgiving break. After Thanksgiving, we will still continue discussing on state space, which is linear system theory. And then there will be a brief, very brief introduction to nonlinear control theory. And this is where the course will end. So please understand, we will have a good amount of material covered in this course. And all this information is super important and a prereq to the Robotics 2 coursework. Robotics, most of you will be taking Robotics 2 in spring. So for Robotics 2, you will need all this information, and Robotics 2 will start where Robotics 2 is ending, which means we will review chapter 8, and then in Robotics 2, there will be hands-on assignments on using root locus for the motion control. Say you will have to control a DC motor using Arduino. So that would be an assignment in the next Robotics 2. In Robotics 2, you will be asked to build a robot arm that will use all this information. So all these codes that you write using MATLAB and Mathematica, please make sure that you understand and you have access to those codes in Robotics 2, because that will save a lot of work. Now, I just want to briefly talk about the homework and quiz schedule. And I would like to give it this in advance so that you can manage your time very well. Some students are taking this class online. Some students are out of state, out of country. So just please make yourself familiar with this information. There are total 4 quizzes and 4 homeworks and 1 additional homework, which is homework 0. Each homework is 10%. Quiz could vary from 10 to 20% depending upon the content. But at the end, the homework will be towards 40% of your grade, and quiz will be towards 60% of the grade. I don't plan on curving the grade. So pretty much what you see is what you get. So this is going to be the homework and the quiz schedule. So please understand, for homework, you will have 1 week, approximately 1 week to complete. And for each quiz, you will have 2 weeks to complete. The way the course is structured, every week, you will have either a homework or the quiz. So which means every week, you will be working on one or the other assignment in the robotics class, either homework or the quiz. So I just want everyone to look at the course structure, and if there are any questions, I would be happy to answer. Online students, please send your questions via chat, and in-person students, you can ask me your question. So does anyone have any question? No questions? Okay, fantastic. Online students or students who have logged in via Zoom, are there any questions related to the course, related to the prereqs, the course expectation? Once again, it's not explicit, it's stated, but I would like to clarify, late homework will not be accepted. So unless you have a valid university excuse, late homework will not be accepted. Okay, so I don't see any questions on chat. So what I'm gonna do is, I'm gonna review the PowerPoint slides. So in today's class, we are going to go through the basics of robotics, the fundamental. These slides are online. They are already uploaded. So you are welcome to take a look at those now or later, or come prepared for the next class. So these slides, they come from the textbook. So the information that you see on the slide is pretty much reflected from the textbook. But as I go on, what I will do is, either I will have my notes written up on the slides, or I will add additional slides. Okay, I see a chat question that you don't see the access to the document. You might have to go to the files, right click and download. And if that is still the problem, I will help you out after the class. So students who are here, do you have access to the information, the material on the slide? Does it on the canvas? Yes. It's what? Unpublished. Okay, I see what the problem is. I will publish that information as soon as the class is done. So you will be able to see that information. So I'll do that immediately after the class is done. So what is this course about? This course is about helping you understand what the robots are, what they do, how they are designed. The field of robotics is really vast, which means you have robots that are humanoids. You have robots that are articulated. You have robots that are used for pick and place machines. You have robots that are used at autonomous ground vehicles or autonomous aerial vehicles. It's not possible to study all the different types of robots. So in this class and in this book, we are going to focus on dynamics of articulated robots. In other words, we will study the robot hands, multi-body system dynamics, and control. When we go to robotics 2, at that time, we will study different types of robots. For example, aerial vehicles, ground vehicles, how their control works. In this first course, we are not going to talk about the hardware as such. So we are going to talk about mostly how the robots work, how to understand how the dynamics work. In the next class, which is robotics 2, we will actually play with the hardware and try to build some robots and use these techniques that we study in this class to analyze, design, and control those robots. In robotics 2, we will also talk about the machine learning and robotic vision. So that chapter is in Niku's book. So we will study that. And in robotics 2, all the information that we study in robotics 1 will be super useful. So what is a robot? So there is a difference between a robot and a manipulator. Manipulator is thing that manipulates. Robot is something that already has the brain and the computer and the control. So you have a system, a subsystem, which is mechanical, that is controlled by a subsystem, which is electronic and which has computers, and it also has sensors. So this integrated system is a robot. And there are different definitions of robot depending upon the country and the standards that you follow. The American definition of robot is a system that can work independently without human intervention. So for an example, if you can program a robot, then robot should be able to carry out that task again and again with the same accuracy. Most of the times, the robots will have some sort of feedback. How the robot interacts with the environment is sensed by the sensors like proximity switches, cameras, accelerometer, gyros, force sensors, or tactile sensors, all different sensors. The robots could be small, the robots could be large. And the field of robotics is vast. And the field of robotics is ever growing. So new concepts are becoming part of the robotics field. For an example, nowadays scientists are experimenting something called as the social robots, the robots that could potentially empathize with human beings and provide emotional supports, robot that could understand human feelings. So the field of robotics is growing, and new frontiers are achieved every time. New discoveries are made, and the scientists are expanding the scope drastically. Now, we want robots to be working with humans. We want robot to be part of humans. So that becomes the wearable robot. We want human and robots working together. So we have cobots. Because as you can see, robot is this huge chunk of machine that is way stronger than the human. So how do you make sure when the human is working alongside the robot, the human is not hurt? So for that, we have cobots wherein they have additional sensors to mitigate the risk to the humans that are working in their workspace. Now, most of the times, the robots are, are actually programmed by humans. But nowadays, the field of artificial intelligence and deep learning is growing to such an extent that the robots are self-programmable, which means there is a concept which is called as the transfer of knowledge. And we will look at examples of the transfer net and this knowledge information in robotics too. But think about like something like this. You have a robot that is watching human motion or human action. Based on that human motion and human action, the computer algorithm, computer actually, you have a stereo camera, that motion is captured, and you have a stereo camera that processes that information, and then those actions are encoded in terms of primitives, and these primitives are replicated by the robot. So for an example, if you have a human, that human is doing something like a simple grasp, what would robot do is robot, just by observing the human, will try to mimic that motion. So that is sort of uh, uh, this is called as transfer learning that is becoming part of the mainstream robotics. Then there is something called as perception. How does robot know where the robot is or how the environment around the robot is changing? So that is called as perception. Then how do we localize? How do we know where the robot is at certain given point of time? Or how does robot know what is in the vicinity of the robot? How does robot behavior change when instead of just one robot, you have two or more robots working together? That is something called as the swarm robotics. So the robotics field is growing, and by the time you graduate, there will be new areas in robotics that will be available and would be interesting. So this is the basic classification of robots. You have something called as the fixed sequence robot. You have something called as the playback robot. You have something called as a numerically controlled robot, and finally you have something called as intelligent robot. And this transition was made possible by the advances in the amount of computing power that we have available. So the fixed sequence robot is like something like pick and place. Pick from one location, move it to the second location, and drop it. Yeah. Oh, thank you. All right. So, can you hear me now? So, the fixed sequence robot is the device that is performing based on the successive stages, like a pick and place machine, wherein the robot is picking and placing, wherein you have very simple operations, but the robots can perform those operations very fast. Now think about converting that pick and place machine into a tic-tac-toe playing machine, wherein the robot needs to make the decision where she should draw either a zero or a cross. Think about one level of complexity. How do we convert that robot into a chess playing robot? Then now the robot not only has to track where the particular piece is placed, but then he has to strategize like what should be the strategy moving on so that he can win the game. Think about the robot that is solving Rubik cube, and again that is also possible. So you will have to have a robot that is, or two robot hands that actually work in coordinated fashion, not just one hand, but you need to have two hands that work in coordinated fashion, and then you can solve the Rubik cube. And again, don't take my word for it. You can just you can watch the videos on the YouTube where you will see all these possibilities that are solved by robotics. How about ping pong playing robots? Students, I mean, the scientists have done that. Now, how about the robot that helps or assists during operations? There is a Da Vinci robot that is used for microsurgeries. So that helps create an environment where the surgeon can remotely operate on a patient. So history of robotics. Again, it started with Rosen in 1922, where he actually coined the word robota. 1946, George Deville, then 1952, all the way 1961, 1962. So that is how the field of robotics evolved. And one thing I just want to tell you, that the history of robotics is very fascinating, because scientists have all these ideas, but then we did not have the tools to make those ideas happen. But very recently, with the Industrial Revolution 4.0, the advent in AI and computer science that enabled us to make all these things possible. and make robots that are smart, that are smarter than the previous generation of robots. And as the cost of computing power started going down, 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 as the size started going down, 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 then we could fit all this massive hardware and computing power in a small footprint. And then that made us make these robots possible. And again, this is the evolution of field of robotics. And what are the advantages and disadvantages of robots? The advantages, biggest advantage of robot is they can work in the environment where the humans cannot. So for an example, if the environment is hazardous, corrosive, or not safe for humans, you can have a robot do the job. For an example, if you want to inspect something, but you suspect that it's dangerous for human, so you can send a robot with a camera, and then you can actually scan and map. Then robots are more precise and repetitive compared to humans. And then robots basically can be worked together or alone, which in some cases it may not be possible for humans depending upon the task, but you could actually use robots for the tasks that are not doable or not safe by humans. Again, the thing is, robot is a machine. As long as the machine is well maintained, they can work non-stop. And then the power, the robot, you can have, it's not possible for a human to lift 500 kilograms, but you could design a robot that could lift very heavy loads. So basically, in the case of wearable robots, you can augment the human performance. Now, again, this is what is argued a lot of times, that robots may replace human workers. And again, there are arguments for and against it, depending upon the industry. In certain industries, it makes sense to use robots. In fact, that improves the productivity. In certain cases, the robot may not be the right way to do it. For an example, if you want, imagine if you want to have some sort of psychological counseling done, and instead of a human being who can express real empathy, you have a robotic voice. That will not serve the purpose. Even though it may be efficient, it may be cost effective, but that will not serve the purpose. Think about how annoyed you get when you are trying to talk to someone in the customer service and you have an automated AI-based voice trying to direct you through the maze to the right customer service person. And you just say, I'm not interested in talking to the AI. I want to talk to an actual human being. So again, robots sometimes can give you wrong answers, because think about, the robots are as good and as efficient as the people who designed and programmed them. So again, robots, even though human robot, we add AI capabilities to robots, but still, if you look at on the primitive level, their capacity is pretty limited. The human brain can do fabulous things that robot cannot. Robots are costly, you need to maintain them, and you need to program them, and so on. So what are the major components of a robot? And here we are showing you a simple articulated robot. So you have a manipulator, you have an end effector. You can think about end effector as something that is used for grasping. So your fingers or hand. You have actuators. So actuators could be motors. It could be maybe DC motors, stepper motors. It could be hydraulic actuators, hydraulic cylinders, pneumatic cylinders, so on. Then there will be sensors. Sensors will be like accelerometer, gyros, vision sensors, proximity switches, and so on. You could have a controller. In the case of controller, you will have some sort of controller algorithm. And when I say controller, there is a slight difference between the controller and the processor. The controller is the control algorithm, is the mathematics or logic that actually governs the behavior. And the processor is the electronic instrumentation that actually implements that mathematical logic. And software is the actual program that takes that controller logic, converts into a machine readable code, binary 0-1 code, and programs the processor. The software also allows the user to reprogram and configure changes to the operating parameters. Now, think about degrees of freedom. So what do I mean by degrees of freedom? DOF, or degrees of freedom. So DOF is number of independent coordinates required to specify state of the system. For an example, if you have a block in the three-dimensional space, this block can translate in X direction, in Y direction, and in Z direction. Assuming this is X, this is Y, this is Z. This block can also rotate about X, about Y, and about Z. So a 3D object has 6 degrees of freedom. So similarly, how many degrees of freedom a robot has? So it means how many independent coordinates are required to specify the state of the robot. So if you think about a very simple robot, so I'm going to call this as a link robot, wherein this is just a link in two-dimensional plane, which is X and Y, and this is an end effector, wherein what we have is we just want to grab a ball from point A. So this is the ball, and kind of move it to point B. So this is point A and point B. So if I want to track the trajectory of the CG of the ball, I need to know where the X, Y location are, or I need to know what is this angle theta and what is this length L. So in other words, if I want to specify this robot or this robot arm, I will need to specify X and Y, or theta and L. So this is a 2 degree of freedom robot. Now, robot could have as many as 6 degrees of freedom. You could have a half DOF, which means the rotation is constrained. And we will look at the different robots and try to identify what are their degrees of freedom and how do we address robots that have more degrees of freedom or less degrees of freedom. How do we derive the motion equations, position equations, and so on. Now, this is a basic thing. Whenever we try to analyze robots can be made up with different joints. So before that, I need to give you a simple definition of a link. So link is an element, link is a mechanical element that has relative motion with respect to other element. So as you can see, I have drawn a simple link. Link is a mechanical element that has with relative motion. Now, when you add two links together, you need some sort of a joint that attaches link 1 to link 2. So this is a joint. Now, there could be a prismatic joint. So prismatic joint is something like this, something like a piston cylinder assembly. So you have a piston and you have, so this is called as prismatic joint. And prismatic joint is denoted by something like this. This is the prismatic joint, wherein it can only support a forward and backward or reciprocating motion. So prismatic joint is again called as a linear because it can go forward and backward. So it can have translatory motion. Now, rotary or revolute joint is where you have one link and other link, they are connected with a hinge. So this joint is a rotary joint. So this is R, this is P. And rotary joint is usually shown something like this. So in this particular case, I can show the rotary joint something like this. So this is R and this is P. In the case of a sliding joint, you could have link 1 and you could have link 2, but the contact in between them is not a revolute or prismatic. It's kind of sliding. So they are continuously making in contact. For the spherical joint, think about your shoulder joint. What you have is, you have a spherical ball and then you have the cap, and then it can rotate in about 3 different directions. They cannot separate, but it can have theta x, theta y, and theta z. So it can rotate about 3 orientations. So we can make different types of robot depending upon the particular configuration. So a very simple example is, think about the 3D printers that we have in the Innovation Hub. They are 3P robots because you have X slider, Y slider, and Z slider. So they are 3 prismatic joints. Think about the robot hand. The robot hand would have combination of prismatic and rotary joints. Now let's talk about briefly what are the different robot coordinates. The robot coordinates, you could have a Cartesian coordinate system wherein you have X, Y, and Z, which means 3P stands for 3 prismatic joints. So robot coordinates P, this becomes P, P, P. So the one prismatic joint, the first prismatic joint, the second prismatic joint, and the third prismatic joint. You could have a cylindrical robot wherein the first joint is prismatic, the second joint is rotary. So the first joint is prismatic, second joint is rotary, and third joint is prismatic. So, and again, what is the significance of these coordinates? Because the way these joints are assembled, so for example, prismatic, 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 it tells us the workspace of the robot. So clearly, if you have a gantry type of robot, now what do I mean by gantry type of robot? wherein you have one slider in X direction, one slider in Y direction, and one slider in Z direction. The end effector, which is the end of the robot arm, the workspace that is spanned by that robot arm is going to be a rectangular or a sort of cubic workspace. So it would be a Cartesian workspace. It's going to be a block. It could be a square block or it could be a rectangular block, but it's going to be a block. If you have a cylindrical robot, then it's going to, if you look at the workspace that is spanned by the end effector, that is going to be a cylindrical workspace. If you have a spherical robot, that means if you have first prismatic joint, second revolute joint, and the third revolute joint, then the workspace that will be spanned is going to be sort of a spherical workspace. Depending upon your requirements, depending upon what you want to do, the workspace is important based on the application, and that dictates what type of robot is to be used. Then you could have an articulated robot wherein you have 3 revolute joints, and the workspace of 3R robot joint is different depending upon how those robot joints are aligned. If they are RRR, something like RRR, they could be something, this would be the first R, second R, and third R. So 1, 2, and 3. So this would be the first R, second R, and third R. And again, depending upon what configuration we have, we are going to study different types of robots, and we'll study them from start to end. So we will talk about how to set up the robotics problem, and then how to find out the position of the end effector, how to find out the velocity of the end effector, and so on. Then there is something called as the SCARA robot, wherein again the same robotic joints, prismatic and Cartesian, they are aligned or they are assembled in a different order. That gives you a different configuration. So this is how those robots look like. So first robot is a Cartesian robot. So what I want you to do is, I want you to see that you have motion in the Z direction, you have motion in the Y direction, and you have motion in the X direction. So if this is the end effector, then the workspace that is spanned by the end effector is going to be rectangular. You could have a cylindrical workpiece. In the case of cylindrical workpiece, you can have, actually I made a mistake here. This is revolute, this is prismatic, and this is the end effector. So this is the base. This is the first prismatic joint, second prismatic joint, and third prismatic joint. Then if you think about the spherical joint, you have the revolute joint, and the prismatic joint. Then the articulated robot, you have the revolute joint, you have the revolute joint, and you have the revolute joint. And if you look at the SCARA robot, you have a revolute joint, and then you have a prismatic joint. So SCARA is R, 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 P. This is P, P, P. This is R, P, P. This is R, R, P. This is R, R, R. So these are different types of robots. Now, one slightly different way of configuration is the delta configuration, or also called as the parallel robot. And I don't know if you have seen some of those 3D printers. The 3D printers, they use this delta configuration. So in the parallel robot, what you have, instead of serial links, wherein the links are connected in series, Here the links are connected in parallel. So as you can see that this link is parallel to the link behind. So you have the parallel robots, so you have series robots and you have parallel robots. The next important point, and we will talk about this in detail, is called the reference frames. So again, we need to understand where the robot is at a given point of time. So there is something called as the world reference frame or inertial reference frame. This is the baseline frame with which all the positions of the robot or robot joints are derived. So this is the world. Then you have something called as the joint reference frame. So this reference frame is not fixed, but this frame is fixed to that particular joint, and that is shown in the figure. Then you could have a tool reference frame, wherein the reference frame is attached to the end effector. And as we talk about the homogeneous transformations in next few lessons, we'll see where these different frames are attached and what are the applications of those frames. But please understand, there is something called as the ground or the world reference frame or inertial reference frame. You have a joint reference frame, which is attached to the joint, and there is a tool or end effector reference frame that is attached to the end effector. Now, programming can be done by multiple ways. You could have a software like MATLAB. You write the program and send it off, or you can write the program in robot operating system or ROS and download the program into robot. Or you could have a teach pendant wherein the human can press buttons and create a program for that robot to execute. Or you could have sampling and some sort of AI that will decipher the primitives and then make robot do that motion. Or you could have some sort of offline programming with simulators like Gazebo, wherein you actually program the robot in the software simulation, run the simulation, make sure that is functioning properly, and then upload that program into robot. Now, the robot characteristic depends upon what the payload that robot is going to support, what is the reach of the robot, how precise that robot should be, the motion should be, and how repeatable the motion should be. Now, robot workspace is determined empirically or mathematically. For an example, as shown below, for a Cartesian robot, you have a sort of a rectangular block. Cylindrical robot, you have a cylinder. The spherical robot, except for the areas where the end effector cannot reach, is pretty much symmetrical. I mean, it's spherical. You could have an articulated robot. And for the parallel or delta robot, this is delta robot. This is the workspace that is shown. So depending upon the type of robot you use, that dictates the workspace. So depending upon the application that you want, you will choose the robot. There are different languages that are used to program robot. You can have a microcomputer based or compiler based, or you could have a structured programming language, or you can have a primitive motion, or you can actually program point to point, and then that when that program is executed, you have that robot motion. Different robot applications, they can be used for machine loading, pick and place, welding, and painting. There are a lot of applications of robot. And inspection, sampling, manufacturing, medical applications, wearable robots, hazardous environment, underwater robots, humanoid robots, prostheses, and collaborative robots are the robots that are programmed to work with the humans. They can detect human presence and then make sure that the humans that are in their workspace are continuously observed and are safe all the time. So when we study robotics, we have to be aware of the implication of robotics on the economic. For an example, whether it will replace workers, what are the economic consequences, the social consequences, and we have to come up with the potential solution. So with this, I'm going to stop. And if you have any question, I have a minute to answer the question. So any questions on the material that we discussed so far? So my suggestion to all of you is next time, please bring your laptops and have MATLAB and Mathematica software installed on your laptops. You can look at my apps and then it will show you, or it will tell you the download instructions. Any questions? The recording will be posted online after the class. So by tonight, I will upload the recording and the slides. If there are no other questions, I'm going to stop the recording.